Hello all, welcome back to Climate Dynamics. In today's lecture, lecture number 6, we're going to be looking at near-surface flow. This extends on our discussion of the general circulation last time by investigating how heterogeneity at the land surface plays out in terms of meteorological fields. The reading for this lecture is Marshall and Plum, chapter 7.4. In this section, we're going to be focusing on Ekman theory. The definitions you need to know are that of Ekman layer, Ekman pumping, and Ekman suction. The key questions we want to answer are: how does surface heterogeneity affect the climate system? How are the dynamics of the near surface different than the dynamics of the free atmosphere? And what is the effect of frictional forces on atmospheric fluid parcels? Alright, let's review what we've learned about the climate system to date. There are several external drivers that are important for producing the climate system that we observe. The first of those is incoming solar radiation, which is of course responsible for providing heat to the planet. In conjunction with the planet being a sphere, this leads to global temperature and moisture distributions that are non-uniform. That is, because the Earth is a sphere, we have more energy received per unit area at the equator than we have at the pole. Consequently, in conjunction with Clausius-Clapeyron, we then know that these warmer regions are able to hold more moisture, and the colder regions are able to hold less moisture. Thus, we have a moisture distribution which matches very closely with the global temperature profile. That is, we have the moistest regions of the Earth located in the equatorial regions, and the driest regions of the Earth located in the polar regions. There's another external driver here as well, which is rotation of the planet. This is responsible for driving the dynamics of the atmosphere. In particular, it gives rise to Coriolis force, which gives rise to geostrophic balance. This then describes the dominant horizontal balance in the atmospheric system. Going back to global temperature distributions, we have that global temperature and moisture are responsible for driving convection in the Earth system. That is, by producing unstable vertical atmospheric profiles, we can have fluid parcels that rise in the background environment. The presence of moisture in the equatorial regions in particular is responsible for destabilizing this part of the atmosphere and giving rise to some of the deepest, most extreme convective regions. We also have that this global temperature and moisture distribution leads to equator to pole heat transport. That is, the major weather systems that we see around the world are primarily the consequence of the Earth trying to redistribute temperature and moisture from the equatorial regions to the polar regions. Through the transport of heat, which emerges through the Hadley circulation and through mid-latitudinal eddies, we have other large-scale features of the atmospheric dynamic system, including mid-latitudinal westerlies and equatorial easterlies, that also emerge in conjunction with the presence of the Coriolis force. These emergent large-scale processes are then responsible for being the primary mechanism for transporting heat and moisture and energy from the equatorial regions to the polar regions, thus smoothing out the global temperature profile. The climate and weather systems that then emerge from this are the focus of the study of this course. We're now going to investigate the effects of heterogeneity. That is, we know that the picture that we saw previously about the general circulation is somewhat idealized. It doesn't take into account zonal variations that can occur because of variations in the land surface. So the idealized picture of the general circulation only really leads us to this profile here. What we know is that temperature has its maximum around the equatorial regions and drops to its minimum in the polar regions. Because of the presence of the Hadley circulation, we have this trimodal peak associated with precipitation. That is, we have a primary peak in the equatorial regions where we have our strongest deep convection, but we also have secondary peaks in the mid-latitudes. These come about because of subsidence that occurs in the subtropics, that is, around 30 degrees north and 30 degrees south, where we have sinking motion that suppresses precipitation. Consequently, the precipitation curve looks a bit more nuanced than the temperature curve here. Nonetheless, it also follows closely with how we anticipate moisture to be present within the Earth's atmosphere. That is, we have a peak of moisture occurring in the equator and dropping to a minimum in the polar regions. The distribution of precipitation then, through this trimodal peak, emerges because of variations in dynamics of the atmosphere. This question of surface heterogeneity, though, is very important because even at the same latitude, we have very different climate regions. Even within the United States, the west coast of the US is very different than the east coast. Analogously, if you look at Europe, you can see that Europe remains fairly snow-free in this particular picture, but looking across Asia at similar latitudes, you see a very snowy scene indeed. As well, we see even in the subtropics variations. In Mexico, we see very green, a very green land surface around the Gulf of Mexico, but at the same latitude in Africa, we have the Sahara Desert. So these heterogeneities are primarily introduced because of variations in surface topography and surface roughness. So we're going to investigate how the dynamics of the atmosphere are affected by the presence of these zonal inhomogeneities. One of the perhaps most common and most well-known features that arise because of surface heterogeneity is the so-called sea breeze. The sea breeze emerges because land and ocean have different heat capacities associated with them. That is, land tends to heat up more rapidly than the ocean because the land surface only has a very thin layer that is exposed to any radiation, whereas the top layer of the ocean, known as the mixed layer, which we'll be studying in future lectures, actually has quite an extensive depth that has potentially exposed to radiation. Further, the ocean can move around, whereas the land surface, not so much. Consequently, the ocean takes a lot more energy to warm up in its near surface layer than the land surface does. Because of this diurnal variation, we have that over land, we get much warmer air. This tends to rise against the background environment and can produce circulation that encircles back over the ocean. Because of the difference in temperatures over the ocean and the land tends to produce lower pressures near the land surface associated with this rising motion that then draws in air from the ocean, producing the sea breeze effect. Consequently, those in coastal regions near the land surface will find wind that tends to blow from the ocean to land, particularly in the afternoon. This is part of a larger circulation depicted here. At night, when the land surface cools more rapidly than the ocean, we actually have a reverse circulation, known as a land breeze. In this case, air from over land blows over the ocean, again because of temperature differences that emerge. Monsoon systems are an example of a large-scale dynamical pattern that really are very analogous to these sea breezes. That is, we have a significant temperature differential between land and ocean in monsoonal regions. This has the effect of drawing in warm, moist air from over the ocean and thus producing convection and precipitation in the monsoonal regions. All right, let's investigate these land surface heterogeneities globally. Well, in the equatorial regions, we've already discussed that we have significant rising motion. This rising motion occurs because of both a warm surface as well as convergence of winds from the north and the south. The convergence of winds occur because of the returning branch of the Hadley circulation, or the surface branch of the Hadley circulation, where air is drawn in order to replace this convecting air. The presence of convection actually pulls air away from the near surface. This has the effect of producing a low pressure region, and this is also one of the main drivers for the drawing in of air in the near surface. The sinking air in the subtropics, on the other hand, is responsible for pushing more air into the near surface. This has the effect of producing high pressure, and high pressure in the near surface will then lead to divergence, that is, wind that tends to move away from that point. You can see that as well in the divergent branch of the feral circulation here, which moves into the mid-latitudes, as well as the northernmost extent of the returning branch of the Hadley circulation, shown in red. This divergent effect then pushes these winds away from the subtropics. However, again, this image is an idealization that neglects the heterogeneous structure of the land surface. If one considers the surface pressure profiles that one actually has in the presence of zonal inhomogeneities, we actually have a picture that looks closer to like this. Here we have the real global sea pressure field, shown as an annual mean climatology. In terms of the presence of lows and highs in this diagram, there is pretty rough agreement with what we saw in the previous figure. That is, we have in the equatorial regions, we have lower pressures than in the subtropics. In the subtropics, we have higher pressures than in the equatorial regions and in the mid-latitudes. In the mid-latitudes, we have lows, And in the polar regions, we have highs. That is, at the very top and bottom of this diagram, we have slightly higher sea level pressures than in the mid-latitudinal regions. But if you look at zonal variations, instead of the high pressure being fairly uniform in the zonal direction, we instead see clusters where you have much higher pressures than to the east or the west of those particular locations. Off of the Pacific seaboard of the US, we see the Pacific High, which is a semi-permanent structure that migrates with seasons, but is nonetheless responsible for driving the dynamic patterns in that region. Over the Atlantic, we have the Bermuda High, again, another feature that migrates with the seasons and is responsible for driving zonal inhomogeneity in the dynamics. In the southern hemisphere, we see three large highs located in the eastern Pacific, South Atlantic, and over the southern Indian Ocean. As well, because of land surface inhomogeneity, we also see over Asia some significant variations in this mean sea level pressure. Again, this is responsible for driving fairly high pressures within these regions that can impact, for instance, precipitation. Recall our discussion of geostrophic balance. If we assume that acceleration is small and friction is negligible, we then find that we must have a balance between Coriolis force and pressure gradient force. This then gives rise to geostrophic winds. Geostrophic winds tend to move along lines of constant pressure. That is, they tend to be at 90 degrees to both the pressure gradient force and the Coriolis force that they're experiencing. In the northern hemisphere, then, this gives rise to our large-scale westerlies in the mid-latitudes. An analogous pattern in the southern hemisphere, except this time with Coriolis force reversed, also gives rise to large-scale westerlies. Applying geostrophic balance to this distribution of pressures gives rise to the wind vectors that we see in this diagram. In the northern hemisphere, we have clockwise rotation around highs and counterclockwise rotation around lows. In the southern hemisphere, the pattern is reversed, with counterclockwise rotation around highs and clockwise rotation about lows. The overall patterns are consistent with what we know about the global circulation, however. We see, of course, easterly flow in the equatorial regions and westerly flow in the mid-latitudes. These two diagrams show wind vectors at the top of the troposphere in the top diagram and in the near surface on the bottom diagram. Notice in the top diagram that we have primarily westerly flow with very strong westerly winds in particular as we get into the mid-latitudes. This is, of course, a consequence of the free atmosphere not having too much frictional effect associated with it, thus allowed to flow faster, as well as thermal effects that we studied in conjunction with the thermal-wind relationship and the diverging branch of the Hadley circulation in conjunction with geostrophic balance that arises because of the presence of Coriolis. In this bottom diagram, however, we of course have much weaker wind speeds. Here, the winds are associated with, are driven by frictional effects. However, we still see the primarily westerly flow in the mid-latitudes and easterly flow in the equatorial regions. Nonetheless, it is clear that the land surface heterogeneity is having a pretty significant effect on the wind fields. You'll notice the formation of circulations over the oceanic regions because of interactions between the low-level winds and topography, particularly topography at the western edge of these continents. As well, we see slower speeds over land, where frictional effects tend to be higher, and larger speeds over the ocean, where there is fewer obstacles to the flow. If one compares these wind barbs with the previous diagram showing pressure, we'll see pretty good correspondence between the locations of these high-pressure centers and the circulations in the flow. Alright, let's study how our understanding of atmospheric dynamics changes in the near surface. We're going to start again with the horizontal momentum equation, which of course relates the velocity of a fluid parcel to the forces that it experiences. Here the primary forces are pressure gradient force, Coriolis force, and frictional force. Recall, in the case of geostrophically balanced flow, we simply have pressure gradient roughly balancing Coriolis force. In the near surface, which we're now studying, frictional forces cannot be neglected, and so are included in this equation. For small Rossby number, as in the case for most atmospheric flows, the curvature is negligible. That is, it accounts for approximately 10% of the total velocity in the atmosphere, and so we'll consider it to be small for this theoretical investigation. This is a good approximation nearly everywhere, except for near regions of very low pressure where you have very strong curvature associated with the flow, including tropical cyclones or tornadoes. In this case, we're going to neglect then the Lagrangian rate of change of the velocity and assume that the flow exists as a balance between pressure gradient, Coriolis, and frictional forces. All right, let's consider for a moment the special case of zero friction. Recall that in this case, we end up with geostrophic balance. Under geostrophic balance in the northern hemisphere, we have a pressure gradient force, which is directed to the left of the direction of the flow, and we have a Coriolis force, which is directed to the right of the direction of the flow. These two forces, when in balance with one another, produce flow along lines of constant pressure. However, in this atmospheric boundary layer region, approximately the lower 1 kilometer of the atmosphere, surface roughness is responsible for inducing turbulence, which then acts to damp out the flow velocity. In this regime, the frictional force can no longer be neglected. So let's consider all three forces together, and consider them in balance with one another. All right. We must still have that the pressure gradient force is perpendicular to lines of constant pressure. This is purely a function of how the pressure exists, how the pressure field is laid out over the geographic region of interest, and is not dependent on the actual flow velocity. On the other hand, the other two forces, the Coriolis force and the frictional force, are dependent on the flow velocity. Namely, the frictional force always acts to slow down the motion, so it is always directed opposite of the direction of flow. The Coriolis force always acts to turn the fluid parcel to the right, so it is always directed 90 degrees to the right of the flow. Putting these together on this diagram, one finds that the only way you can have a perfect balance between the three forces is to have a flow which is slightly directed towards the low pressure region. That is, the frictional force, in essence, works in conjunction with the Coriolis force to balance out the pressure gradient force. Since we have two forces that are now opposing the pressure gradient force, it is generally the case then that the pressure gradient force must be larger than any individual force. So the Coriolis force is weaker than it was in the geostrophic case, and so we must have that the flow is directed slightly towards the low pressure region. In essence, this means that in the presence of friction, pressure gradient force tends to win out. That is, pressure gradient force, which is acting this whole time in order to bring fluid parcels towards low pressure regions, is now able to do so. It now is able to direct the flow somewhat towards the low pressure region. This layer is known as the Ekman layer of the atmosphere. It's where the frictional forces cannot be neglected, and where in the fluid, the flow is the result of the balance between pressure gradient, Coriolis, and turbulent drag forces. If one considers both the geostrophic and ageostrophic component of the flow, where the geostrophic flow comes from the balance of the pressure gradient and the Coriolis force, we can then substitute this geostrophic component into the equation above, and this then indicates that the ageostrophic component of the flow must be introduced to perfectly balance the frictional force. And in fact, the ageostrophic component must be at exactly a 90-degree angle to the frictional force. Observing from the diagram below the alignment of these various vectors, that also means that the ageostrophic flow is exactly opposed by the Coriolis force. That is, they're two vectors that point in opposite directions of one another. The total flow velocity is then the sum of both the geostrophic and the ageostrophic components, with the ageostrophic component then pointing, again, opposite to the Coriolis force, roughly in the direction of the pressure gradient force. In this particular arrangement, one then has that the sum of these three forces equates to 0, as shown in this triangle diagram on the left-hand side here. In total, the net effect then is the typical flow then is directed slightly towards regions of low pressure. The consequence for this in the near surface then is, in regions of low pressure, you tend to have convergent flow, that is, flow tends to move into the low. And for high pressure regions, we have divergent flow. That is, we have flow that moves away from the near surface high. Recall back to our discussion of the general circulation. Where were the regions of low pressure? Where were the regions of high pressure? Do these correspond well to the locations of the circulation cells that we know about in the general circulation? I'll give you a chance in order to think about that. All right, these are two typical diagrams showing Ekman flow, one around a high pressure on the left and the other around low pressure on the right. In the high pressure arrangement, we have flow that is directed slightly outside of the high, that is, it tends to diverge from the high, and in the low pressure, we have flow that is directed inward, that is, it tends to converge towards the low. Around the high, fluid tends to fall away from the center, but around the low, it falls towards the center. Recall again, this occurs because in the near surface we have frictional effects that are responsible for opposing geostrophic motion. The net result, if one traces the trajectory of these fluid parcels then, is to see in the high pressure case a fluid parcel that spirals out away from the high, whereas in the low pressure case you have a spiral into the low. The spiraling, of course, occurs because the flow is still mostly geostrophic. That is, it tends to try to follow along these lines of constant pressure, but with a slight inward tilt associated with it. Here are two real photographs showing a rotating fluid tank, both for the case in the top of a local low pressure, where we have fluid parcels that are falling into the low pressure region, and on the bottom, where we have a central high pressure region. This effect can be very easily demonstrated by using this rotational fluid tank, and we again observe results very consistent with those in the atmosphere. In the top image, where we have a central low, the fluid tends to fall towards the center, tracing a path in the purple. In the bottom image, we have fluid that falls away from the center. That is, it tends to move in a spiral pattern away from the center, or diverges from that central high. Here's a depiction from windy.com of April 19th, 2020 at 9 p.m. GMT, showing a region just to the east of Japan. This particular image was chosen because it shows both a prominent high and a prominent low. Pay close attention to the individual fluid parcels in this diagram, here depicted with the white streaky lines. Well, how do you see them behaving around the high? How do you see them behaving around the low? If you pay close attention here, you'll notice that around the high, these fluid parcels are tending to diverge away from the high. That is, they're not following along lines of constant pressure, but instead appear to be directed away from the high slightly. Similarly, around the low, we see fluid parcels tend to spiral around the low before converging towards the low itself. That is, we have a tendency for fluid parcels to be directed slightly inward toward the low. You can check out these effects yourself on windy.com. All right, let's return to our discussion of subgeostrophic flow. Recall, we can take the normal wind and decompose it into both the geostrophic and the ageostrophic wind speed. It turns out that the ageostrophic wind is typically very small compared to the geostrophic wind. That is, it only tends to have about 10% of the magnitude of the geostrophic flow. Ageostrophic flow tends to be strongest over land, where the drag is large, and at low latitudes where the flow departs from being in geostrophic balance, that is, where the Coriolis parameter is small. Alright, so recall in Introduction to Atmospheric Dynamics that we actually showed that the geostrophic flow is non-divergent on pressure surfaces. That is, if you're going to take the horizontal divergence of the geostrophic wind on a constant pressure surface, you can show that that is exactly equal to zero. And in fact, you can show it in about 3 lines, as in the top of this slide. However, the ageostrophic flow does lead to horizontal divergence. That is, if you take the divergence of the ageostrophic wind, the value is non-zero. We already saw that actually on the previous in the previous discussion, namely, in the case of a local low, we had convergent motion. That is, the ageostrophic wind tended to push air into the low pressure region where we had then convergence of the flow. On the other hand, if we had a high, we then had ageostrophic wind that was directed away from the high, leading to divergence of the flow. This has important implications for vertical motion within the fluid, because if we return to the continuity equation in pressure coordinates, we see that the vertical gradient of the vertical pressure velocity, omega, is actually going to be equal to that divergence of the real wind on constant pressure surfaces. This plays out as follows, and kind of makes sense if you think about it intuitively. In the near surface, if you have converging motion, then that wind needs to go somewhere. And what's going to happen is it's going to produce upflow, or updrafts. That is, it's going to generate upward motion as a result of the convergence, because again, the wind has to go somewhere. If we have a local high, then we have divergent motion, and that wind needs to come from somewhere. And the most natural place for it to come from is to be drawn down from above. So in the case of divergent motion, we then have that we must have a downdraft above the location of the high. So taking the expression for U in terms of geostrophic and ageostrophic wind, namely that U is just the sum of the geostrophic and ageostrophic wind, and plugging it into this continuity equation, we actually find that the vertical motion is purely driven by the horizontal divergence of the ageostrophic wind. All right, so again, what does this mean? Well, in the case of surface lows, that means that we must have convergence of the flow. Convergence of the flow is negative divergence, so the right-hand side of this equation is then going to be positive. What does that mean? Well, di W or di omega di P is proportional again to di W di Z. Recall, because pressure decreases as we go up, and omega is proportional to negative W. Consequently, that must mean that we must have upward motion that is induced when we have a surface low. And since di W di Z is going to be equal again to, or proportional to, negative of the divergence of the ageostrophic wind on pressure surfaces in the presence of a surface high, we would have that the right-hand side of that expression, namely the negative divergence, will be negative for a surface high. This then induces downward motion in the case of a surface high, or it pulls air down from above. All right, here's a depiction of kind of what is going on. Recall, once we get away from the boundary layer, we're in the free atmosphere, and in this region, the flow is approximately geostrophically balanced. That means that if we have a column of, for instance, low pressure, then we would have rotation about that low in the free atmosphere. However, in the Ekman layer, in the near surface region, we instead have convergence. That convergence then drives upward motion through that fluid column. This is associated again with cyclonic rotation about a region of low pressure and surface convergence that induces upward motion. In the case of a near surface high, we have divergent motion that is then responsible for pulling air down from above. So it sucks air down from the upper levels and produces a downdraft in order to fuel that local high. Again, recall back to our discussion of the general circulation. We have lows located in the equatorial regions. This is, of course, associated with rising motion, so everything here is nice and consistent. And we have highs in the subtropics, which is associated with regions of subsidence. So again, things here are consistent with between pressure and the regions of rising and sinking motion. There are particular terms given to the rising and sinking motion induced by these local variations in near surface pressure. In the case of a convergent motion driven by a low, this is what's known as Ekman pumping. That is, the near surface layer is pushing air to higher altitudes or pumping it up. Whereas in the high, we have what is known as Ekman suction. That is, this local high is sucking air down from above. So more formally, Ekman pumping is associated with low surface pressure, is upward motion above the Ekman layer that is driven by near surface convergence, and Ekman suction, on the other hand, is associated with high surface pressure, is downward motion that is associated with near surface divergence. In regions of Ekman pumping, that is where we have updrafts, we have cooling of air parcels on ascent, which can of course drive possible condensation. So we can have clouds and precipitation forming in these regions. Whereas in regions of Ekman suction, we have of course warming of air parcels in accordance with the dry adiabatic lapse rate as they're pulled down. That is, there's not going to be a whole lot of condensation occurring because of course the air parcels are warming, which is increasing their saturation-specific humidity. Consequently, regions where we have Ekman suction are associated with clear skies and suppressed precipitation. All right, so with that in mind, let's turn again to this this depiction of the mean sea level pressure. Of course, we have lows in the equatorial regions, so that's associated with lifting motion. This, of course, makes sense as this is the rising branch of the Hadley circulation. In the subtropics, we have subsidence associated with near-surface highs. This is, of course, associated with sinking motion, which is along the subsiding branch of the Hadley circulation. In the subpolar regions around 60 degrees south and north, we of course have lows. These are associated with lifting motion along the polar front. And then in the deep polar regions, we have high pressure, which is associated with subsiding motion. This is the subsiding branch of the polar cell. All right, so everything seems to work out quite nicely. We see this consistency then between mean sea level pressure and the global circulations. All right, so here are the distributions then of near surface pressure shown on the top, taken as a zonal mean. We have lows again in the equatorial regions and in the subpolar regions around 60 north and south, and highs in the subtropics and in the deep polar regions. From what we know about geostrophic balance, we have that zonal wind speeds are going to be proportional to the meridional variation of the pressure field. Recall this was important in understanding thermal wind balance as well. But with this in mind, we know that wherever we see the pressure tending towards higher pressures, that is, if P di y is positive in the northern hemisphere, that should be associated with easterly flow, and where we see a reversal of that, namely if we see dp dy negative in the northern hemisphere, then that should be associated with westerly flow. So looking at the 10-meter zonal wind speed or the near surface zonal wind speed here in the bottom diagram, our westerlies again correspond to regions where we have a poleward tendency towards lower pressures, and easterly flow in regions where we have a poleward tendency towards higher pressures, as anticipated. In conjunction with where we anticipate there to be convergence and divergence in the low pressure regions, again, remember this is associated with Ekman pumping, associated with near surface friction that is responsible for directing fluid parcels towards the low. We have convergent motion. The bottom plot here shows the 10-meter meridional wind speed, and as expected, we see convergence of the meridional winds around the equator, around the intertropical convergence zone, but we also see other regions of convergence around 60 north and 60 south, again where we have these low pressure regions in the near surface. And if you look for regions of divergence, we see that around the subpolar regions, around the subtropics at about 30 degrees south and 30 degrees north. All right. That's all for today. Thank you very much. Next time we're going to start talking about the global oceans.